closely linked to both the principle of absolute spectral tone color and the principle of the multiple missing fundamentals, local spectral coherence helps to explain the perceptual process that connects the absolute spectral tone colors of simple sounds and the tone colors of the spectral peaks of a complex sound. If we consider the second, third, and fourth harmonics of the pitch A3, their frequencies will be equivalent to the pitch of A4, E5, and A5. Now I've chosen this pitch and these harmonics because the absolute spectral tone color of each one of these harmonics is different. A4 is like an U, E5 is like an O, and A5 is like an AW. We can change the amplitude of each harmonic to effectively reshape this spectral envelope. Now, if we make it flat, so that all three harmonics are the same amplitude, the sound is what I would describe as something that is less than O. It is the majority of the sound that we would call O when we actually listen to it in context. When I add it back in, this vowel will become O again. Now I'm going to manipulate the amplitude of each one of these harmonics to reshape this segment of the spectral envelope. First, we'll shape it in a way that favors the second harmonic of A3. This harmonic has an absolute spectral tone color of U, and this sound will be something that is less than U. If I reshape the envelope to powerfully favor the fourth harmonic of A3, then the sound will be something that is less than AW, which is the absolute spectral tone color of this highest harmonic. If I reshape the envelope to favor the middle harmonic, the less than vowel quality is still going to be O, just as though it were completely even. Why this sounds like O, but also this sounds like O. Are they slightly different? Yes. But are they both most like something that sounds like O? Yes. Now the reason behind this is a concept called the spectral centroid. Now you could take the spectral centroid measure of this entire spectral envelope, and basically the question that it's asking is, what is the average brightness of the spectrum of sound? What you do is you add together the frequencies of all the harmonics, you incorporate into the equation how loud one harmonic is compared to its neighbors, and you come up with a weighted average for the entire spectrum. If you do this with just a segment of the spectrum as well, you'll come up with an average frequency center for just those harmonics. This specific case is pretty easy to calculate the spectral centroid because the amplitudes are all the same, so we're just going to use the number 1 for the amplitude. And these harmonics happen to have whole number frequencies. The second harmonic of A3 has a frequency of 440 Hz, the third has a frequency of 660, and the fourth has a frequency of 880. What we do is we multiply each of those frequencies individually by their amplitude. In this case, we're just going to use the number 1. We then take all of those answers and we add them together, and we get the number 1980. We then divide that number by the sum of all of the amplitudes, which in this case is 3, and we get the answer, which is 660. So the spectral centroid of these three harmonics, all at the same amplitude, is the same frequency as the middle harmonic. By changing the slope to make it sound more like ooh, effectively what we've done is we've moved the center of gravity for this segment of the spectrum to a lower frequency. That lower frequency has the vowel-like color that is closer to ooh. And you can see, simply by raising the amplitude of one of the higher harmonics, we can destroy the ooh. That was enough to tip it over to sound like a less than O. The truly remarkable thing about this perceptual process, however, is that all of these less than vowel colors were perceived at the pitch A3. Local spectral coherence is the way to explain how the individual absolute spectral tone colors of all of the harmonics in the spectrum of the voice cohere into spectral peaks, and the tone color of those spectral peaks is then represented in the perceptual space of the pitch as a missing fundamental.